Well, that's cool, Natalia. I'm happy for you doing that, kind of nerd out on an article a little bit, right? So let's look at ANOVA. Okay, this is really big, big scary stuff. Okay, and I'm just warning you guys now, so that when you look at it, you're not overwhelmed. The lucky part of us running out of time is I'm not going to make you do these calculations. Okay, so so don't stress about that. I'm just going to want you to definitely know these definitions, be able to talk or answer questions and understand what is ANOVA, what are they comparing, what are they doing, why do we use it, and at the end, what conclusions can we draw, and what do we do in an instance where we get to reject the null hypothesis with an ANOVA. Okay, so just kind of understanding the why of it all. So I'm going to minimize us over here real quick just so we can read this. So analysis of variance, that's what ANOVA is, this acronym for, okay? And it's an inferential statistic that we use to compare means, okay? And we've been doing that all along. We've been comparing means even from the Z-score, definitely in the t-tests, and now we do it again in analysis of variance. This one we compare variances, okay? Now in the Z-test, we were given population standard deviation. In the t-tests, we would estimate population standard deviation, and then we would calculate a standard error, okay? In ANOVA, we need to, instead of it just finding like one number, one standard deviation, one standard error, in ANOVA, you will have at least two variances that you will be comparing, okay? And then we're gonna assess interactions, okay? And we're gonna look at how our groups can interact with each other. So there are a couple different types of ANOVA. We will, in our class, go over what we call a one-way ANOVA, okay? And a one-way ANOVA is a hypothesis test of two or more population means, okay? And it's in an independent samples design. Now, we discussed what independent samples mean. Think back to the t-test. Independent samples is when they are two different groups of people, okay? This is not paired in any way, okay? So these are two separate groups of people. Here it says you would do it with two or more groups. Honestly, we hardly ever see people just do a one-way ANOVA if you only have two groups, because in that instance, you could do a t-test. And a t-test is a whole lot easier than an ANOVA, okay? So really, you see an ANOVA being done as soon as you have three groups or more, okay? Or three or more levels to the independent variable. Okay, and we'll talk about that in just a little bit. Okay, so ANOVA uses F. I don't know why it's called F. Well, that's not entirely true. It's probably like because it's like factorial, but they use the F distribution. This is just theoretical sampling of F values. Okay, we can compare this definition to the T distribution, which was a theoretical sampling distribution of T values, okay? And what that means for us, this is where we find our critical values, okay? We find F ultimately by dividing what we call MS treat divided by MS error. And we know F to be a ratio of variances. Okay, so these are kind of like two important little maybe definitions or something. These are important right here. If I know anything in my history of teaching statistics, a test will ask about this. Okay, so I just want to put that there, and I'll explain this in just a minute. Okay.
And just a question. So the F distribution in ANOVA is used to find the critical value?
Well, no, and I was thinking that as soon as I talked about this, and so it's like I can read your mind, Natalia. I know exactly. So this is just something different. This, like, in fact, it shouldn't even be a sub. Let me see if I can do it. I don't know where. There we go. It should not be a sub bullet, if that makes sense. It's, you know how we use a t-test, or we use a t-distribution to find critical values, but
Yes.
then we also ultimately calculate a t.
Okay.
Right? That's what the difference is. This, we use an F distribution to find the critical values, but how we ultimately find F is, this is the calculation.
Okay.
If that, does that help a little?
But the similarity is that the critical value is found by this method.
No, the critical value is found, no, not by this formula. We don't have a formula for critical value.
Oh, okay. No, but like by the F distribution, I mean.
That's right. And look, I'll show you right here. In fact, I didn't even put all the pages up here. There are several pages to the F table, okay? And as you can see, the F distribution is even more complex than the T table. So everything about ANOVA is like statistics put on steroids, okay? So even, you can even see here with how we find the critical values, it's even put on steroids, okay? So we still use, we still just find the critical values, you know, kind of, sort of in a similar fashion. I'll explain this in a little bit. And so that's how you find the critical values. And then when you go through all the calculations, ultimately, F is found by this simple formula, okay? But this is very misleading because there are about 2 or 3 other formulas before you get to this simple one, okay? And I'll show you that in just a little bit. So does that help it out?
No, it does clarify that there is, it's the distribution that finds the critical value, not the actual F.
Right.
The F is the F, you find the F in order to find the critical value.
Or your F obtained, if you want to think of it that way, right? Yeah. So the F test is this part, okay? If you want to think of it that way. And the F distribution is how we find our critical values. Yes.
Okay.
And thank you for asking that and clarifying that, because I promise you, as soon as I was talking about it, I was like, okay, this is confusing. So thank you. Thank you for asking.
You're welcome.
Okay, let's look at this part real quick, and I'm gonna explain this MS treat and this MS error, okay? So and these are kind of flip-flopped. I don't know why it did it this way, but that's okay. First, it talks about the denominator of F, and I'm gonna write it up here. So if you remember, F is equal to MS treat, and that's just short for treatment. And this the denominator is error and the numerator is treat. I wrote it right, I just didn't say it right. Treat stands for treatment, and error is often used as another way of describing variability, right? If we think of the amount of error or the amount of deviation from the norm, okay? So they just like to use that word. So the denominator of the F, okay, is an estimation of variation, right? And it's sometimes called an error term. All right, so that's how we have this right here, error. There are authors, there are books, and perhaps, of course, professors that might call it within. Okay, so sometimes you see it written like this. And this is actually how I learned it. So that says between, and then this says MS within. And I'm writing them both down, and I like how this author explains both of them, because I think maybe it just kind of adds to understanding. So the MS within is we're looking at the variation within the group. Okay, this one up here, the MS, is looking at the variation between the groups. So let's think about it this way. If we were evaluating the reaction time of adults, teens, and kids, we know that not all adults are going to have the same reaction time. Not all teens will have the same reaction times, and not all kids will have the same reaction times. So the MS error, or the MS within, looks at the variability within the group of adults, or it looks at the variation within the teenagers and within the kids. So it accounts for that error that not all kids are the same, not all teens are the same, not all adults are the same. The MS between, or if we want to think of it as treatment, also you could think of this as the levels. Remember that from way back at the beginning of the semester when I was saying levels or treatments are just the groups of your independent variable? This one is looking at the difference between the groups. What's the difference between adults versus teens? What's the difference between adults versus kids? And teens versus kids? This is the one where it's ultimately looking at what's the difference in their mean scores, say, of reaction time. I want to see y'all's faces now.
Hold on.
Okay.
I'm highlighting.
Oops. I'm going to move you over. You need to think about it for a little bit.
Could you repeat it?
Yeah. So the within, they're looking at the error or the variation within the adults, right?
Okay.
Some adults are going to be really fast and some are going to be really slow. Some teens are going to be faster than some of the adults, and some teens are going to be slower than some of the kids, right? And you're going to have all this variability within each group. Okay. Right? The between is the one kind of like what we could think of what we were doing with our t-tests and with our z-scores. We were comparing ultimately the means of the groups, right? We were saying, okay, what's the average of adults compared to the average of the kids? Or what was the average of, you know, I don't know, these group of kids when we compare them to...
So like the wait, sorry, is it
Or this one, the numerator?
The numerator is talking about like, you know, if you're comparing between adults, teens, and kids, while within is like comparing group of adults, like between ages of this and then between this range of ages? Is that what it's doing?
Yeah, I think you could think of it like that, right? Like if we think back, remember our t-test was the mean of one group minus the mean of another group.
Okay.
And then we ultimately looked at this, divided it by this standard error down here. This, or whatever this was down here, this might be oversimplifying it, but that's okay. So this one little formula that we did down here was looking at the difference of all of those groups. Remember,
Okay.
we did that big formula and we were
Yeah.
figuring out the standard deviation for those groups. So this is always some measurement of error between our groups, okay, or our variation between our groups. The top part in statistics, this part, is always comparing the two groups. It's almost like it's ultimately what you want to be doing, right? It's what you're interested in. This is what you're trying to figure out, right? Did
Yeah.
IQ go up? Did weight go down? Did stress levels go down? I don't know, whatever it is, it's ultimately what we're interested in. The cool thing about statistics is we're always using some form of variation to kind of control for that, right? We want to say, hey, we know these groups are different, but we want to make sure that we're taking into consideration all the differences that exist within the groups. Okay, so we were doing it all along, we just didn't explain it this way. Okay, we were always looking at the differences that exist within the groups, and then we ultimately were comparing two groups up here. Why we talk about it here is it just gets more complicated. We're no longer just looking at two groups. We now have three, okay? And so not only are we going to have to look at all the differences and these combinations that we can have adults versus teens, adults versus kids, and then teens versus kids, okay? And so there's all of that going on where we could be looking at over here, right? We're looking at like adults versus teens versus kids, okay? And then down here is, well, we're looking at the variation within all the adults. We're looking at the variation within all the teens.
Yes, that's what I mean. That's exactly what I was trying to say, within the actual group. Because
That's exactly right.
The other one is between, like comparing
versus.
adults, teens, and kids.
Yes, that's exactly right.
But one is, when we're talking about like within, is within the group of adults, within the group of teens, within the kids. Yeah,
that's
what
exactly
I
right.
was referring. Yes.
Okay. Yeah. So that's exactly what that is. Okay. Okay. Is everybody good on that? We're good on that so far? Okay. So, all right, look at this craziness. So this is, and you guys are so lucky. I used to make all my, every class up till now, I have made everybody, we would spend so much time doing all of this stuff, okay? It looks really scary. It's actually not as bad as it looks. And just kind of like with the independent samples t-test, right? He looks big and scary, but he's not that bad. So it just depends on how many groups you have, right? If you have like 4 or 5 groups, oh my gosh, I mean, your numbers they just goes on forever. Talk about tedious. So in this example, they're comparing drug A, drug B, and drug C. Okay, so we have our 3 groups. They're labeling them that way, right? So this is what that means, right? XA, XB. They're squaring them just like what we were used to, okay? They're summing them, they're summing the x's squared and so on, okay? They're doing it for the B group and they're doing it for the C group. okay? So they got the sum of x's and sum of x's squared. They got the means for each group, okay? Now, I don't know what they're evaluating here, but let's see, in our house this morning, we all woke up very sniffly, sneezy, swollen eyes and stuff like that. So we're all suffering from allergies over here, maybe from that rain, I don't know. So maybe this is these are allergy medications. Okay, and so maybe they're asking us to report our allergy symptoms. Okay, and so a higher score is more allergy symptoms, and a lower score could be lower allergy symptoms. Okay, so these are our means. Okay, now there are there are several other numbers we're not used to getting, right? This one right here is looking at, we need a value usually that is sum of x total. And as you can see here, you just add up the sum of x's. Okay, so they took 27, 29, and 9. And then we need a sum of x squared total, okay? And so then they take the sum of x's and they add all of those up, okay? Then we get to these formulas here, our SS's, okay? Our SS's are the big kind of nasty formulas. This is what scares everybody down here. And this is what they're doing. Now, I want to point this out right here. Do you see how this one says SS drugs? And this one says SS error. So what they did, instead of writing SS treat, which we would be used to seeing, they substituted it and put drugs in there. And what they're doing is they're just labeling it and almost making it a little bit simple so that you know this is the comparison of the groups, okay? SS treat or SS drugs. Not all books, not all authors will do that, but this one would be the one that would be the treatment, okay? They're just kind of telling you these are the levels, okay, the different drugs. So these different formulas here, again, these are all, you know, obviously if you were to do it by hand, how you would calculate this. The SS total is a really easy one. You're just using these two numbers here, your sum of x total and your sum of x squared total. And you put the bigger number there minus the smaller number squared divided by n. Look at this formula right here. This is very similar to what we've been doing all along, right? We saw it like this. It would be the sum of x squared minus the sum of x squared divided by n, right? It's not, we don't get the square root of it because we're dealing in variances, right? So we're not taking square roots of all of this stuff. This one here, whenever you see something like this, this looks big and scary, but he's just saying add them all up. And this one, you can see here, they have little t's, okay? This is just kind of, in my head, I think of it as saying like, do this for each group, or get the sum of x for every group, the n for every group, or each group. So if you see here, what they're doing is they're taking the sum of x for this first group right here, this 29, they're going to square it, and then they're taking the n for that group, which is 4, okay? And then they're going to add it up and they're going to do it for the second group. They're taking that 27, they're squaring it and divided by n, or yeah, n, 4, and then they do it for the last group, okay? Ultimately, they subtract off some of our total over here, okay? And then you get this formula down here, the error. And again, if you see this one, it's like what we've been calculating all along, okay? Without our little house. So what they're doing is they just do that very familiar formula that we've been doing for standard deviation, and they're going to now do it for each group. Okay, so this is like drug A group, drug B group, and drug C group right there, right? The 219 minus the 29 squared divided by that. Okay, so as you can see, once you kind of break it down and see, you know, more or less where these numbers come from, it's not terribly difficult. It's just tedious, and you want to make sure you're always putting the numbers in the right spot, right? So that's kind of the hardest part of this. But again, take a deep breath. We're not having to calculate any of these things. Okay.
Just correct me if I'm wrong, but is the SS error like kind of comparing within the drug A, drug B, and drug C groups?
That's exactly right. Yeah, the SS error is the variation within each group.
And then the SS drugs is what exactly? It's just comparing the between?
Yeah, it's looking at like what is the sum of X's for each group, and then they're going to take it out of the total. But I guess I'm kind of thinking like of in terms of averages here, like they're averaging the
Okay.
the square, like they're kind of getting the average, like looking more or less at the mean or the average of the X's of the individual values
Okay.
for each group. So yeah, in some way or another, with my kind of limited ability to explain that, but they are ultimately looking at like 29. I mean, if you do 29 divided by 4, that's the mean for this group, right? So
Yeah.
they're comparing the means in this one. Yes, essentially is what they're doing. SS total really doesn't matter. We don't even, when we're ultimately calculating everything, it does not even come into play. But we use it as a check system. Okay, so let me show you this part now. Actually, I'll skip right here and I'll show you this one. So SS total is just equal to SS treat plus SS error. Okay, so we just put this here just so you would know this. This is, so really we don't use SS total. It doesn't go into any calculation as far as helping us find our F value, but it serves as a nice check system. Okay. I'm going to show you the source table here. So these are the numbers that came from here. Okay, we had 84.917 for our SS total. We had 60.667 for SS treat, and we had 24.25 for SS error. And those are our same numbers here. Okay, so we call this a source table for ANOVA. Okay. And a source table is kind of a little cool thing, okay? Because as soon as you get these values here, you're pretty much done. I know it doesn't look like you're done yet, but these are the hardest numbers to calculate. And once you have them, everything else flows really smoothly, okay? So here's our SS treatment, or our SS drugs, SS error, and SS total. And one thing that we just saw on that slide is that we know if you add those up, you get the 84.917, okay? Now, we know this one, right? We know this guy, degrees of freedom, okay? As you can imagine, and as you've already learned, degrees of freedom has changed a little bit. Like with independent samples t-test, we learned of something called degrees of freedom total. Well, just like all the other stuff, when you look at ANOVA, degrees of freedom is also put on steroids. Okay, so now we have 3 measures of degrees of freedom. Okay, and I'm going to write down these formulas here because I didn't put this on the slides. So let's do that real quick. So degrees of freedom treatment, I'm going to stay with treatment because that's the most generic term, okay? But we know right here they're using drugs. And so they're using like they might say DF drugs, right? This one is found by, it's K minus 1. Oh my gosh, what? I lied to you, right? I always said it's always going to be N minus 1. Well, in this instance, it's not. Okay, it's K. K in statistics is equal to the number of levels of the independent variable, AKA also known as groups, right? How many groups do we have? So in this example, we had 3 groups, right? We had drug A, drug B, and drug C. We had people that took drug A, drug B, and drug C. So we had 3 groups. So this one would be 3 minus 1, which is where we get the 2. Okay. Cool so far? I don't want to mess these up. Error. Oh, yeah. Okay. So then, let me see, I write too big. Well, that's okay. Degrees of freedom error is equal to in total minus K. In total minus K. Let's get, we haven't talked about anything as far as in total, okay? In total, we didn't do in, or they didn't list them. Conveniently, there was 4 in each group, okay? If you were to calculate in total, you just add up all the ins, okay? So 4 plus 4 plus 4 is equal to 12. So in total, in this example, is 12, okay? It's how many people are there totally in the study, okay? The total number of people in the study. That's in total. So in this example, we would have 12 minus K. Remember, K was 3. We had 3 groups, and that's where we get 9. Okay. Degrees of freedom total is easy. It's just in total minus 1. It doesn't really matter to us. In total minus 1, so it'd be 12 minus 1, and that's where we got the 11. This one doesn't really, we don't use it either. It just serves as a check for these two, because just as with our SS, the same thing works for the degrees of freedom. Degrees of freedom treatment plus degrees of freedom error will equal degrees of freedom total. Okay, these will add up. These will add up, and these will add up. Okay. I will, I'll write out all of this, guys, and I'll include it on a slide for you in here nicely, okay? For you to look back at. I'll have the formulas for degrees of freedom. Any questions right here so far? No?
What was K again?
Number of levels, right up
Number-
here.
Okay, so it's
Number of groups.
3. Oh, okay, 3, yeah.
Right, we had 3 drug groups.
Yeah.
Okay, yeah. So K is the number of levels to the independent variable. Okay, or group, how many groups do you have? Or you're comparing, okay?
Yeah.
Okay. All right, we're doing good. whether you agree with me or not, we're doing good, I promise. Okay. Don't you like it when people tell you? You're like, wait, I don't know if I'm doing good. I know, I'm sorry. Okay, all right. Now, MS, right? We know MS, this stands for mean squares. These are called our sum of squares, and this is our mean squares, okay? These values, our MS, is found by, look how cool this is. How cool, hold on real quick. Oops. Oh, okay, let's see. I'll move you guys over here. Okay. See, I'm gonna get a different color. Green is good. Okay. MS is found by taking degrees of freedom, or I'm sorry, SS divided by degrees of freedom equals MS. Isn't that cool? Let's see. I don't know if we can see that one very well, or maybe it's just because the little. So SS treat divided by degrees of freedom treat will equal MS treat. And then the same holds true for down here. SS error divided by degrees of freedom error will give you MS error. So in this cool source table, this is why I say this table is kind of cool, is you can add down and you get your totals, adding down, right? And across you divide, okay? And then remember how we found F back in that other formula? I'm going to erase this real quick, I think. If you remember, let me make him a little smaller, he's going to be too fat. F was equal to MS treat divided by MS error. So, right, the 30.333 divided by 2.694 will equal F. Take a deep breath. Remember, you don't have to do this. I'm just showing you how these source tables work. Oh, oops. What in the world? Let me see your faces. How are you doing? Cassandra's okay. Natalia, do you like it or not?
I'm just trying to figure it out.
You're taking it in?
Yeah, I'm taking it in.
Okay. So, and it's, you know, being in class is so much easier. Like, I guess as we're calculating it, when we get SS error and or treat and we plug it in there, and then we get SS error and we write the number down in there and we just add them up and then we get that number, right? Once you see it already typed out, it just, I don't know, it kind of loses something, right? If you did it on your own, you would be like, oh, that's where that comes from, okay? Our degrees of freedoms. We got those values.
You
Okay.
divide the SS divided by the degree of freedom to get the MS for the drugs, and then you do the same thing for the bottom, and then you divide those two MSs by each other to get the F value.
That's exactly right.
Okay, that's not that bad.
Yeah, it's really, I don't know, I just kind of like these source tables. Like, they're just kind of cool, you know. Whoever thought of this is like, oh wow, that's fun, right? You can add up those two columns and then you can divide across and you get those values, and then just divide those last two, the MSs, to get your F. Okay. Now F is a really big, this is like our F, this is like our T, right? When we'd get our T value and we'd do like the drum roll and we'd want to see if it exceeds our critical value, this is F. So this is kind of the end of it. This is where, oh, let's see if it is significant or not. This table, he put it in here, he's already telling you that, that it is less than, the p-value is less than 0.01. So we already know that this is a significant test, okay? And in fact, he's listing it for you right here. He's saying F at the 0.01 level with the degrees of freedom of 2 and 9 is equal to, I guess, 802. I'll take his word for it, but let's check it out just in case.
Excuse me.
Yes.
Teacher, I'm gonna have to go because my daughter, something happens to my daughter.
Oh,
so
no.
I will watch that video
Okay.
today. I'm sorry. Okay,
No.
I watch it because this is very hard for me, but I'm gonna have to. Maybe tomorrow I will connect. Okay.
Yes. Okay. Don't stress. Okay.
Thank you. Thank you.
Okay. I hope everything's okay.
Thank you. Bye-bye.
Bye-bye. So I'm going to show you now how to work this table. I'll try and make it a little bigger here. Okay. These are the alpha levels of 0.05 and 0.01. The F distribution doesn't have all of those other alpha levels like we had in the T. Remember in the T, there was 0.1, 0.5, 0.025, 0.05, 0.01, right? There was lots of them. Here, they're only dealing with 0.05 and 0.01, okay? The light face, these up here are the 0.05s. The bold are the 0.01, okay? So now how we read this is these numbers across here are the degrees of freedom for the numerator. I don't really like how it says it like that, just because I don't know who thinks in terms of numerators and denominators. I always, and in my book even, I have it listed as up here is degrees of freedom treat, and on the side is degrees of freedom error. Okay, so if we look back at our example, our degrees of freedom treat was 2, and our degrees of freedom error was 9. And that's why he has those listed right here like this, 2, 9. That means that we come here to 2 by 9 right here. This square is our 2 by 9, okay? The light face is 0.05. The bold face is 0.01. If your F value is bigger than 0.05, it's significant. If it's bigger than the 0.01, that's even better, right? It's even more significant. So 11 blows away the 8, right? It far exceeds the 0.01. And that's why he has it listed here. That's why he went with the 0.01, right? That's why he says here that the chance or the probability of finding an F at 11.26 is less than 0.01. Okay. If say our F was only like a 7 and it did not exceed the 0.01, it's still significant, right? We still found a significant result because it exceeded the 0.05, right? In statistics or in social sciences, we go with the 0.05. This is good enough for us. This is good. It's not even good enough. This is good, right? But of course, if you have a value that even exceeds the 0.01, we'll go with that too, right? Because we know, oh, wow, that's really good. Okay, so I don't want to confuse you on that, on why he listed here the 802 and went with the 0.01. You certainly could do the 0.05, or you know what I mean? That's still significant. Okay. This is why I say that these numbers don't really matter. The reason they don't really matter is, if you notice, we didn't even use them. They do not go into the calculations to find F. The only things that we use to go into the calculations of F are all of these values, right? So these don't really matter, okay? They are listed in a source table for us. They serve as a check, okay? And it tells us, oh, there's 12 people. Like, you can just look at some of these things and just go, oh, okay, that's what that is. But these are your big numbers here. These are the ones that matter, okay? Because they're ultimately used to find our F. This is why right here, in our, when we say like what our results are, we could do something like 2 common equal 10.26 with a p less than 0.0. That's how you would write that in symbolic notation. We did an F test. Our 2 important degrees of freedom were 9. That's a comma, not a dot. Our F was equal to 11.26, and we ultimately found our P was less than 0.01. You know, of course, you could put 0.05 there too. Okay. I know this is a lot. I know it's a lot to take in. Here's another example. And as if doing 3 groups wasn't fun enough, you could do 4 groups, okay? You could do 4 groups that, look at this one. There's lots of, this N was 7, right? The other N's were 5. This N had more, this group had more participants or people or whatever it is. This example is looking at and testing Skinner's reinforcement schedules. And so down here are all of their calculations to find their S total, their SS treat, right? Remember here, he just put schedules because those are the different groups, or those are the different treatments. And then our SS error, okay? We could look at this really fast and see how everything turned out for this ANOVA, okay? They got an F of 17.16. I think by now, knowing that when we have an obtained value that's really big like